Namaste, my friend, and welcome back to JEE Physics with Typical Monk. This is class 9, and today we look at something you touch every single day without noticing. The fact that nothing in this world is perfectly rigid. Push a wire, pull a spring, twist a rod, and it resists. It stretches a little, and then it springs back. Push too far, and it never comes back the same. Sarah once assumed a thick steel rod simply would not bend at all, and lost marks on a question that was really about how much it bends. Every solid has a story written in one curve, how it stretches, how it yields, and how it finally breaks. And here is the G delta over neat. The energy stored inside a stretched body is found by an integral, not a shortcut formula, and composite wires need the same careful bookkeeping as a circuit. Take a slow breath. Let us begin. So what will you carry home from today's class? First, stress and strain, and Hooke's law, which holds only within the elastic limit. Second, the three moduli, Young's, bulk, and shear, one modulus for every kind of deformation a body can suffer. Third, the elastic potential energy stored inside a stretched or compressed body. Fourth, Poisson's ratio and thermal stress. This is the calculus-flavoured G delta that NEET quietly skips. And fifth, the stress strain curve itself, and the G drills built entirely on what you learned today. Ready? One idea at a time. Let us start with the two quantities everything else is built from. Stress is the restoring force spread over unit area. Force divided by area measured in Pascal. Squeeze it, stretch it, shear it, the units never change. Strain is the fractional deformation it causes, change in length over the original length. Notice it has no units and no dimensions at all, because it is one length divided by another. Now Hooke's law. Within the elastic limit, stress is directly proportional to strain, and the constant of proportionality is what we call Young's modulus. Y equals stress over strain. David used to think Young's modulus, bulk modulus, and shear modulus were three unrelated formulas to memorize. The day he saw, they are simply the same ratio, stress over strain, applied to three different kinds of deformation. He never confused them again. Look at this curve carefully, because every material tells its whole life story along it. From the origin up to point P, stress rises in a straight line with strain. This is Hooke's law in action, and the slope of that very line is the Young's modulus. Just past P sits the elastic limit, point E up to here, remove the load, and the body returns exactly to its original shape, no matter how many times you repeat it. Cross point E, and the story changes forever. At the yield point, E, the material begins to deform permanently. Remove the load now, and it stays bent. Stress keeps climbing to its highest value at point U, the ultimate stress. And then, the material thins at one spot, a process called necking, and finally snaps at the fracture point. Lisa once assumed a dimensionally correct-looking formula for this curve had no real shape to it, until she saw that this shape is exactly what the experiment measures, point by point. Now, three ideas that sit just beyond the basic law, and G loves testing all three. Poisson's ratio is minus the lateral strain divided by the longitudinal strain. It tells you how much a wire thins sideways as it stretches lengthwise. The elastic potential energy stored per unit volume is 1/2 of stress times strain. Geometrically, it is just the area under that straight line on the stress-strain graph. Thermal stress appears when a rod is clamped at both ends and then heated or cooled. The stress that develops equals Young's modulus times the coefficient of expansion times the change in temperature. And notice it never depends on the rod's length or area. And here is a trap John fell into. Stress is not pressure. Pressure is always normal to a surface and pushes inward equally in every direction. But stress can be tensile, compressive, or shearing, even though both share the same units. Time to solve a full G numerical together, slowly, the monk's way. A 10 kg mass hangs from a steel wire of length 2 meters and cross-sectional area 1 square millimeter, and the Young's modulus of steel is 2 times 10 to the power 11 Pascal. Find the elongation and the elastic potential energy stored. Step 1. Write down what is given. The load gives a force of 100 newtons, taking G as 10 meters per second squared. Length is 2 meters. Area is 1 times 10 to the power minus 6 square meters. And Young's modulus is 2 times 10 to the power 11 Pascal. Step 2. The formulas. Elongation delta L equals FL over a I, and the elastic potential energy stored equals 1/2 times F times delta L, which is the same as 1/2 stress times strain times volume. Step 3. The elongation. Delta L equals 100 times 2 divided by 1 times 10 to the power minus 6 times 2 times 10 to the power 11, which is 200 divided by 2 times 10 to the power 5. That gives 1 times 10 to the power minus 3 meters or 1 millimeters. Step 4. The elastic energy. P equals 1/2 times 100 times 1 times 10 to the power minus 3, which is 0.05 joules, or 5 times 10 to the power minus 2 joules. Step 5. The answer. The wire stretches by 1 millimeter and it stores 0.05 joules of elastic potential energy. Notice the method. Given. Formula. Elongation. Energy. Answer. The same 4 moves solve every elasticity numerical G can ask. Now the 3 moduli side by side, because G always wants you to pick the right one for the right deformation. Young's modulus E equals stress over strain, and it belongs to a wire or a rod that stretches or compresses along its own length. Bulk modulus B resists a uniform squeeze on volume. Apply pressure from every side, and this is the only modulus a fluid, gas, or liquid actually possesses. Shear modulus G resists a change of shape while the volume stays the same. Picture the top face of a block sliding sideways while the bottom face stays fixed. All 3 share the same unit, Pascal, yet each one answers a completely different question. Does the length change? Does the volume change? Or does the shape change? John used to apply Young's modulus to a squeezed gas and wondered why the answer made no physical sense at all. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. Young's modulus I equals FL over a delta L, with dimensions ml to the power minus 1 t to the power minus 2, the same dimensions as stress and pressure. 2. Elastic P per unit volume is 1/2 stress times strain, which can also be written as stress squared over 2y, a favorite substitution in numericals. Number 3. Thermal stress, Y alpha delta T, depends only on the material and the temperature change, never on the rod's length or its area. 4. For wires in series carrying the same load, elongation simply add. For wires in parallel sharing a load, the strain stays common while the load splits between them. 5. A gas or a liquid has only a bulk modulus. A fluid at rest cannot resist a shearing force, which is exactly why it flows. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. A wire with a larger cross-sectional area shows a smaller elongation for the same load. Reason. The elongation delta equals FL over I is inversely proportional to the area R. Think like Sarah, check the assertion, check the reason, then the connection. Both are true, and the reason is exactly why the assertion holds. Option A. Second one, assertion. A rubber band has a much smaller Young's modulus than a steel wire of the same size. Reason. A rubber stores more elastic potential energy per unit volume than steel for the same stress. Both statements happen to be true, since a smaller EI does give a larger energy for a fixed stress. But does the reason explain the assertion? No, the amount of energy stored does not decide how stiff the material is. The causation runs the other way. Both true. Reason does not explain. Option B. This is the trap that catches John every time. Third one, assertion. The bulk modulus of a perfectly incompressible liquid is 0. Reason. For an incompressible fluid, the volume does not change under any applied pressure. Check the reason first. True. An incompressible fluid truly keeps its volume fixed. Now, the assertion, since bulk modulus is minus delta P over delta V by V and delta B goes to 0, the bulk modulus actually goes to infinity, not 0. Assertion false. Reason true. Option D. A quick match now. Say each pairing aloud before I reveal it. Young's modulus pairs with a longitudinal stress over longitudinal strain, the stretch or compression of a length. Bulk modulus pairs with volume stress over volume strain, a uniform squeeze on volume. Shear modulus pairs with shear stress over shear strain, a change of shape at constant volume. And Poisson's ratio pairs with lateral strain over longitudinal strain. How much a stretched wire thins sideways. If all four came to you before the reveal, the three moduli have truly become yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Gases possess a bulk modulus but no shear modulus. Hold your verdict. Statement 2. The bulk modulus of a material is always smaller than its Young's modulus. Think carefully before you answer this one. Statement 3. Strain has no units and no dimensions. Remember what strain actually is, one length over another. So, how many are correct? Two statements, the first and the third. Gases truly resist only a volume squeeze, and strain truly is a pure ratio with no dimensions. But the second one falls. Whether bulk modulus is larger or smaller than Young's modulus depends on the material's Poisson's ratio. It is never a fixed rule. Two correct, and the middle one is the trap. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. Stress and pressure are the same physical quantity, since both are force per unit area with the same units. It feels so natural, same formula, same units, so why not the same thing? But here is the truth. Pressure is always normal to a surface, always compressive, and the same in every direction. Stress can be tensile, compressive, or shearing, and it can act along a chosen direction. Same units, completely different character. Myth 2. A thicker wire stretches less under the same load, so it must have a higher Young's modulus. The truth, Young's modulus belongs to the material alone, not to the wire size. The thicker wire stretches less only because delta L equals F all over I falls as the area R grows. Y itself has not changed at all. One myth, one full G question. Do not let it be the one that costs you. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. What are the dimensions of Young's modulus? Same as stress, ml to the power minus 1, t to the power minus 2. Question 2. What load stretches a 1 meter wire of area 1 square millimeter with y equal to 2 times 10 to the power 11 Pascal by half a millimeter? Using F equals y a delta L over L. The answer is 100 newtons. Question 3. What is the elastic P per unit volume for a stress of 2 times 10 to the power 7 Pascal and a strain of 1 times 10 to the power minus 4? 1/2 of stress times strain gives 1000 joules per cubic meter. Question 4. What is the thermal stress for y equal to 1 times 10 to the power 11 Pascal, alpha equal to 1 times 10 to the power minus 5 per degree, and a temperature change of 100 degrees? Y alpha delta T gives 1 times 10 to the power 8 Pascal. And question 5. The thinker. What is the theoretical range of Poisson's ratio for an isotropic elastic solid? From -1 up to 0.5. If you caught that one, you have truly understood today's class. Let us gather the whole class in one slow breath. Stress is force over area. Strain is change in length over length. And Hooke's law holds only within the elastic limit. Young's modulus governs a change in length, bulk modulus a change in volume, and shear modulus a change in shape. One law, 3 deformations. Elastic potential energy per unit volume is 1/2 stress times strain, and the total energy stored is 1/2 F delta L. thermal stress, Y alpha delta T, appears only when expansion or contraction is physically prevented. And the stress-strain curve carries a material's whole story: proportional limit, elastic limit, yield, ultimate stress, then fracture. And next class, we step into fluids, fluid mechanics, pressure, buoyancy, the continuity equation, and Bernoulli's theorem. The same patient, one step at a time thinking, now applied to things that flow. And so, my friend, we have measured the honesty of a solid. It bends, it remembers, and it tells you exactly how far you can push it before it breaks. Through stress, strain, and 3 moduli that will not lie to you if you read them correctly. Sarah, David, Lisa, and John all stumbled somewhere in today's class, exactly as you might have. And every one of them came out the other side understanding it fully. Be patient with yourself. Tonight, revise the 3 moduli once, slowly: Young's for length, bulk for volume, shear for shape. One idea at a time, you will crack G. Of this, I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the fluids.